started with a continuation of discussion about multiple regression. So you'll recall that what we've been focusing on thus far over the last 4 or 5 weeks has been using regression as a way of predicting the future. And we're going to continue with that, except instead of using just scores to predict other scores, we're going to use a time frame to predict something will happen in the future time period. And this is called trend projection. And trend projection is built on a fundamental idea, which is just this. The more things change, the more they stay the same. That is going to be important, and that's going to explain something in this next slide, because you're going to remember something that I've talked about previously and say, wait a second, that seems like a bad idea. I thought we weren't supposed to do that. And the reason why this will actually work is because we're using time. And the assumption that we have about time is that as things churn along, they pretty much stay the same as they did in the past. The past being a good predictor of the future. So trend projection then is, we look at the past, and if a time series, if a period of time exhibits a linear trend, then a least squares regression analysis may be used to determine a unique trend line forecast. So a least squares regression is one that minimizes the mean square error between the trend line and the actual observed values in a time series. So if we unpack that, we're going to be looking at dots. We're going to be creating a line that runs through those dots. But those dots are going to represent, let's say, sales at different time periods. So we're going to create a straight line that runs through those dots. We're going to find the line that fits those dots the best, and then we're going to extend that line out into the future as our prediction. Now that's where you might say, I thought we talked about this and said that we should not extrapolate outside of the range, in which if we have x values that run within a certain range, we shouldn't try to predict beyond that range. And that is true, except in this case, we're not using x values to predict y, we're using time to predict y. And that becomes a very different thing. So it's the idea that the more things change, the more that they stay the same. The thing that we are using to make our predictions, the predictor, the independent variable, is time. And so we're going to assume that as time goes along, the things that have happened in the past are going to predict the things that happen in the future. And what we're initially predicting are the observed values in our time series. So we create a line that predicts what we already know. And then we're going to extend that line into the future to say, here's what we think will happen based on what has happened in the past. That's trend projection. So we're going to start with a linear trend regression. And this linear trend regression uses a formula that may seem unfamiliar at first, but as you look at it, you'll see that these elements, the parts that make up this equation, are very similar to something we've seen not too long ago when we looked at the equation for a straight line. So we remember the equation for a straight line was y hat equals a plus bx, where a is the constant and b is our coefficient that we multiply by the x value. And when we look at this equation, we see that the y and the x have been replaced by t, where capital T is the linear trend forecast for a period of time, which we create as a lowercase t. And then t is the time period. So the other two elements of this equation are the coefficients of the prediction. So for instance, b sub 0 is still the intercept. It's still a constant. And b sub 1 is the slope. It is the number that is multiplied by our time period. So we have the same elements of this formula that we had as we were using linear regression, but now we've substituted t for the x and y values. It's going to work exactly the same way. So for example, we take a look at some sales. This is sales of bicycles that have occurred over the last 10 years. And we create, using the least squares regression, we create a straight line that runs through the middle of all of these dots. So we can plot these as a scatter plot. And then we can create a straight line that runs through them. So we have years 1 through 10, the sales in each of those years, and we have created a regression equation of 20.4 plus, and then we have the coefficients that are being multiplied. This allows us to predict what will the sales be in year 11. So we've simply plugged in an 11 instead of a 10 and used that as our time frame, and that then makes our prediction. So this is how we predict what will sales be like in the future. So this would be like simple linear regression. We start with data that we already know, we create a straight line that runs through them, we predict into the future, but what we know about the past is that things are not always constant. Sometimes things change, but in a constant way. So we get into seasonality and patterns and trends that occur that we will want to then work into our predictions. Sometimes, especially when business is going well, we'll have a curvilinear trend. So the curvilinear trend, you see the dotted lines that I've added in this example. If I tried to create a single line that explains the data, neither one of those dotted lines is very good. The dotted line that runs through 1 through 5, it starts missing the scores in 6 through 10. And the same thing is true. The line that runs from 5 to 10, it doesn't predict very well for years 1 through 5. So what we have here is a curvilinear trend. So what we would then do is introduce an exponent into our predictive model, and then that will predict a line with a curve in it that will capture this curvilinear relationship between time and revenue. So as we look at our equation, we still see the t sub t, so that predictive value is a constant plus a coefficient times time, and then a coefficient times squared. You immediately think of New York and Times Square. This is times squared. It is any value, anytime we square a value and we put that into our regression equation, we're going to get a curve in the line. Now, if that curve were to curve one direction and then curve back another direction, we could actually use another coefficient, which would be x cubed, x to the third, and that would create a second curve in our line. So without those exponents, we just get a straight line. Add one exponent, we get one curve. Add a second exponent, we get a second curve as well. And as you can imagine, we start getting some very complex modeling when we start introducing those kinds of ideas. So what I want you to know is that if the relationship is not linear, we have ways of modeling that. And the simplest way is to introduce this squared value, this squared exponent, into our equation. So let's talk about the patterns that may emerge as we look at our data. Seasonality and trends. Changes that occur with the seasons and changes that occur over time. So to the extent that there is some seasonality to our prediction, we want to be sure to include that in our forecasts, because things that are true in the first part of the year may not hold up in the later part of the year, but they may reemerge again the next first part of the year. So we need to include those ideas if we're going to make our models accurate as we're forecasting. So we're going to take a look at two examples of this. The first one is seasonal time series with no trend, and the second is a seasonal time series with a trend. So the first one we'll look at is without a trend. Seasonality. These are the sales figures for our umbrella sales at the umbrella company. What do you notice about the pattern of umbrella sales over the 4 quarters of the year? Well, as we look at these numbers, we see there's no long-term trend. If you were to draw a line through the middle of all of those dots, it would stay horizontal. So there's no long-term uptick or decrease. It's consistent over time. However, within those time periods, we see great variability. In quarter 1, in quarter 3, those values are close to the mean. But in quarter 2, we'll say the springtime, we see an increase. And in quarter 4, the sales tend to be at their ebb. So we see in different quarters different amounts of sales. Overall, no trend, but there is a seasonal pattern within these data. How would you predict that? So what we do here is something called dummy coding. A dummy coding, the word dummy refers to dumb as in mute, as in does not sound, does not speak. And here we're looking for the data that do not speak to the equation. We're coding those data as ones and zeros. You know that anytime you multiply a number by 0, your result is 0. So we're going to create codes of ones and zeros, and we'll plug those into equations. And what that will give us then is predictions in which 1 or 2, in this case we'll have up to 3, of the quarters are silent, leaving us with a prediction when, let's say, quarter 1 is speaking. If we have 4 quarters, which I guess we would always have, right? We will always have 4 quarters. So if we have 4 of any units, you need n minus 1 dummy codes. So in this case, 4 quarters, we need 3 dummy codes. That is where we assign a 1 to the quarter that we are wanting to hear speak, and zeros to the others. So we start with the same regression equation. You'll notice that the 95 plus 29 times, all of those are the same. What we are changing is the coefficient to 1 and 0. For quarter 1, we have 95 plus 29 is assigned a value of 1, and the remaining values are assigned 0, so they drop out of the equation. So in this case, only quarter 1 is speaking. In quarter 2, that value of 29 drops out, and we're only listening to the 57 as our predictor. And the same is true for quarter 3 and quarter 4. In quarter 4, all of them are silent, and we're just using our predictor, our constant. So what I want you to take from this is that when we have seasonality, the way that we adjust for that is we use dummy codes, ones and zeros, so that we're listening just to one group at a time in our regression equation. Another thing that can occur is we get the seasonal pattern, but we get a trend over time. So over the years, our sales are slowly increasing, or maybe our errors in production are slowly decreasing. So there's this trend that occurs over time, but we also see the seasonality occurring throughout the year. So what we could do then is plot these 2 years, one on top of the other, and we can look for the patterns. And what we see is in this example, the height of the sales occur around August and September. We have a dip in the spring, April and May, and we see a dip there. So we do see the seasonality, but we see that in this case, year 2 is lower than year 1. So there is a trend that is occurring over time, but no matter what year it is that we're looking at, we see the same seasonality occurring within a particular year. So there's one other idea that I should clarify for you. It's easy to think of seasonality as referring to the 4 seasons, or the 12 months of the year, which is not necessarily, it doesn't have to be about those 4 seasons. So there may be sales that are unrelated to the weather, unrelated to the changing of the seasons of the fall and spring, but they still may occur depending upon other events that are happening during the calendar year, but they're not necessarily tied to the literal 4 seasons of the changing of the weather and the climate. So let's talk more about the seasonality with a trend. I'll use an example here with television set sales, where there's this seasonal pattern, then upward linear trend, more and more televisions being sold over time, but the sales of televisions may increase during certain times of the year. The one that immediately springs to mind is the Super Bowl. in the early part of the year, so we're in January, there is an increase in the sales of big screen televisions. Well, that's a seasonal change, and not related to the 4 seasons. Doesn't matter what the weather is like in January. This is related to something else, but it happens at the same time every year. So we see that increase or that spike. So here's how we would plot this, our seasonality with a trend. Notice that the regression equation, where we have the coefficients in the quarter 1, 2, 3, 4, right? It has the same consistent pattern as we've seen with other regression equations. So we're making our prediction, in this case I'll just call it y hat, equals a constant plus B1, B2, B3 related to quarters, and we can plug in the dummy variables, 1s and 0s, to hear those quarters speak or cause them to remain silent in our prediction. So quarter 1, if time period T corresponds to the first quarter of the year, it gets a 1, otherwise it gets a 0. And that same pattern occurs for quarter 2 and quarter 3. Leaving us then with an estimated regression equation that we could use to predict our sales. So we plug in what quarter is it, and the last coefficient, which deals with the time frame. We have our constant. We can then make a prediction. So in the second quarter of next year, what do we think, how many televisions do you think we will sell? We'll be able to make that prediction using this equation. So there are changes that occur over time, and no matter what those changes are, there's a way of modeling those changes using a regression equation. So this last area that we want to explore, I like the name, time series decomposition. I don't know, it just seems kind of Star Wars to me. It sounds like something that would be a minor plot point about we've got to be sure to make it to this next area before there's a time series decomposition that blows the ship apart. But unfortunately, it's not nearly as exciting as that. It really just has to do with separating out time frames. So when we separate these time periods, these time series into their components, we decompose them. So decomposition methods assume that the actual time series value at any given t time frame is a function of 3 components. Those are trend, seasonal, and irregular, which we could refer to as error. So far, we've talked about seasonality, so the changes within the year, trends, which are changes that can occur over multiple years, and then there's an irregularity, or an error value, that we want to account for in our equation. So now we're combining all of these ideas, and essentially we're saying how much of the change in sales is due to the trend that we're seeing over time, how much of it is due to the seasonal shifts, and how much of it is due to this unexplained irregularity or error. So the combination of the 3 components to make a prediction depends on whether you assume that the relationship is additive or multiplicative. Additive or multiplicative. And the only difference will be whether we're using a plus sign or a multiplier in between the elements of our prediction. So let's take a look at one example. This is an additive model. So what we see is our prediction equals the trend plus the season plus those irregular values, those error values. So this is the predictive model that you would use where seasonal fluctuations, those that occur within the 1 year time frame, are not dependent upon the level of the time series. We're just adding them together because these could occur at any given time. This multiplicative model, and notice the change. It's trend times seasonal times irregular, which then allows us to explore more of the interaction between those terms. So nothing has changed in the terms themselves. We still have trend, we still have seasonal, we still have irregular, but we're using a multiplicative model to make a prediction because the seasonal fluctuations tend to grow larger as the sales volume is increasing because of a long-term linear trend. So we're seeing larger changes over extended time that is increasing the sales volume, and the seasonal fluctuations tend to move along with those long-term linear trends. So this is something that as we were to plot our data and we were to think about what is happening within our multiple years of data collection, we would then be able to look at the trends as they're occurring and make our decision about what is the best type of model to use to make predictions about how many televisions or other objects will be selling for any given time frame. All right, so any questions, anything else you want to know about what we've discussed so far? Thank you so much for being here. I will see you guys next week.